Welcome, everyone. People are coming in and we can also get started. So welcome everyone to our 24th webinar here at InterVenture. My name is Ivana and today with us is our dear colleague Goran Čeko. So welcome, Gorane. Thank you so much for joining. Novi Sad crew will also join because as I told you, Goran, you are a household name in Novi Sad. So people know about you, but we're very excited that you're joining. So thank you so much for your time. And today's topic is going to be what to crack, how to achieve a super fast JVM startup. So we'll be open for questions. Obviously, we'll have a Q&A at the end, but guys, I will be looking at the chat. So if you have anything during the tech talk, please feel free to write and I will just swoop in and tell Goran. Before we can get started, I just wanted to dive in and give a little bit of introduction to InterVenture for all of you who are new here, for all of the people who will be looking at this video also on YouTube. So InterVenture is a Swiss-Serbian software development company specializing in building and operating full dedicated all-star engineering teams with members such as Goran. Together with our partner, we develop amazing software solutions in a variety of industry and covering also a variety of tech stack. Besides that, we also offer a fast and flexible project-based collaboration designed to address more temporary engineering needs, project work, unexpected peaks, or if you just need expertise in a specific field. If you would like to learn more about InterVenture, please feel free to write me. You should have my contact also in the webinar registration email. But this video will be recorded and on YouTube, so you will also have the contact there. Without further ado, I would say we can get started. So Goran, you can share your screen, enjoy the talk. And yeah, I'm gonna mute myself finally and thank you so much.
Thank you. Sounds great. I hope you can see my screen.
Yes.
And that you can hear me. Great, thank you. Okay, so let's get it started. Remove these commands and today, this webinar will give you an overview of Project CRaC and show how it helps improve performance for Java-based applications. So we're going to dive into JVM behavior and see how it can be improved. As we all work in the world of microservices, where that's a common standard architecture for Java-based applications. Everything is running in the cloud, and for those use cases, the JVM warm-up and startup time can become a limit, or it can be an obstacle. So let's say if we are running or starting a JVM application locally and it takes about 5 to 10 seconds, that might not be a big issue for us, but what about production? If it takes a minute or more, then we might want to dive into that. So what's Project CRaC and how does it help us? It's a new OpenJDK project, and it aims to address the JVM warm-up problem with a slightly different approach. So the basic idea is to take a snapshot of a running JVM, then store it in a set of files and then restore it at some later point in time or even on some other machine. With cloud environments where we spin up new instances, it's usually done according to the increased load, so when we want to scale up. And then if there's a slow startup time, that can cause more issues. Of course, native images are just one solution to this problem. They are great and they are statically ahead of time compiled code, does not need to be warmed up, and it has a really instant and short startup time. But with this short startup time and like really small memory footprint, it does not come without any drawbacks. In general, the overall performance might be a bit slower or drastically slower than JVM applications because it's missing JIT optimizations at runtime. So one of the great things, and that's what I would like you to remember from this webinar as a first point, is that the JVM is able to adapt the performance of the Java application running inside of it according to the way how it is used. So it can figure out how this code gets used, how frequently it's used, so it can not identify the hotspots, and then it can optimize the code by its ability to compile code just in time, which is known as JIT compilation or JIT compilation optimizations. So that's great, but it has to figure out those parts first and then to compile it into faster code that requires time. You cannot simply run your code and then assume it's going to run as fast as possible. It also takes some additional resources, and this happens almost every time when the JVM is started. So how does CRaC help us with this? It significantly improves the JVM performance because it shortens these warm-up steps, or it completely eliminates them. And without CRaC, the performance of Java application is always the same across multiple runs. So this new feature, coordinated restore at checkpoint, actually provides a fast or instant startup with immediate performance for Java applications. And one principal use case I'd like to state here is that it's very good for Java applications that perform a lot of work during startup, or that have to be restarted frequently, and then we want to reduce that. So therefore, it's also called sub-second startup or super fast JVM startup. First, I would like to make a slight comparison between OpenJDK and Project CRaC. So OpenJDK is an open source implementation of the JDK, and it contains the source code for the most important components like the Java virtual machine, popularly known as the hotspot, also the Java class library, and the Java compiler. So as it provides the source code for the Java development kit, still you need to have a binary distribution of this JDK to run an application that's compiled into bytecodes. Project CRaC, on the other hand, is just one of the 73 projects that the OpenJDK is home for. It's an open source project that's proposed and led by Azul Systems, which also provides OpenJDK builds. The most famous is the Zulu build, and versions JDK 17 and JDK 21 of Azul Zulu builds contain CRaC features. So CRaC implementation is not part of the official JDK yet. There are some early access builds that provide these features. And if we want to compare OpenJDK versus its builds, it's similar to what Linux is versus its distributions. So let's see how the Java code gets executed and how CRaC fits into the whole picture. So as Java developers, we first start from the source code. We write the Java files. Then using the Java compiler, we compile it into class files to get the bytecode, which contains instructions for a virtual machine. And that can be run on any platform with JVM. Then the class loader loads this bytecode into JVM memory, and from there on goes into this execution engine. It contains of several components that are crucial and that are want to analyze this code that's loaded into memory and to optimize it. And the first one here is the interpreter. So the interpreter, as its name says, it actually interprets and converts the bytecode into equivalent native instructions that can be executed on a CPU. Then another important component is the profiler, which constantly profiles and monitors how our code gets executed, and then tries to identify some hotspots, so code or methods that are frequently called and executed, and then passes it on to one of these just-in-time compilers. So there are two, C1 and C2, previously known as the client and the server. I will show later on what's their main purpose. But in general, the goal is to get better performance than interpreting the bytecodes every time. But still, C1 And C2 compilers depend on the hotness of the code. So it really depends how this code is used. And JIT compilation takes time and takes resources. So here's how the execution cycle looks like. So I will recall what I've said previously, that the great thing about the JVM, the Java Virtual Machine, is the fact that it can adapt the performance of Java application running inside according to the way it is used. But it also has to identify these parts first and then compile it into a faster code. So we start with the interpretation with level 1, which can be slow. It's not that fast. The profiler then analyzes code and monitors for some hotspots. Once that's a certain threshold with the number of times a method is called and executed, it's passed on to the C1 JIT compiler, which is very fast, but does not perform a lot of optimization, so it's quite a low, quite simple optimization, some basic level on level 3, and then the profiler continues running in the background, analyzes the code, and then when the second threshold is exceeded, then the code is passed on to the C2 JIT compiler, which is of course, puts more CPU overload, and its output is highly optimized code that can be executed directly on the CPU. So we can imagine this through a simple example where there's a method that calculates some numbers and then returns the result based on some if condition or some else branch. And if it figures out it always hits the if condition, it can then return this static result every time, so it does not have to compile the code every single time it gets executed. But it's all great until it hits the different branch, unexpected one, unpredicted one, and then the optimization needs to take place when the code execution hits this branch that's not expected. Here's a quick or a simple timeline how it looks when we start a Java application. In the first phase, the JVM itself is started, it's initialized and loaded, and that usually happens very fast. Then in the next phase, the application itself starts. The JVM loads its classes and then initializes resources, performs some optimizations, and the application is ready to be used. And that's what we typically refer to as the time to first response. So we can send a request to that application and get something back. But that does not mean that this application is properly warmed up. So it does not have what happens in the third phase of this timeline, which is the application warm-up. So it's actually the warm-up time is time to reach its peak performance, and it might range from several seconds or minutes, but also can go up to hours or even days. During that phase, the JVM optimizes code, as I previously mentioned. It performs this execution cycle, and the app itself can apply some specific workloads. So to, let's say, fill in some caches or fetch some external data, etc. And this is the whole time, and the time span of this is typically referred to as time to end operations. So without CRaC, this startup time is always the same across multiple runs. So let's see what CRaC concepts are and how it can improve the speed of starting an application. So checkpoint and restore actually allows running app to be paused and then restarted at some later point in time, or even on another machine. So to explain it simply, we have a running application, then we take a snapshot of the running JVM state together with everything that's inside. And so that's what we call the checkpoint. It's a complete state of the warmed up application at some point in time, like a snapshot or like an image. And that's saved to a set of files, to a directory that's specified in some configuration parameters. And those files contain literally everything. So it contains the heap, the threads, the states, and like the classes, all objects, JIT compiled code, and everything around the Linux process information. So essentially, the full process context is saved. So everything that is relevant for the restore phase that will happen later on. The closest thing to compare with this is the heap dump. So you can imagine that the size of this will be something similar to the heap dump, and the bigger heap this application has, the bigger the checkpoint files will be. So it's important to mention that this checkpoint is being created after all the heavy lifting is performed. So after loading classes, after JIT compilation, after some code optimizations, etc., and then we serialize it on the disk on a set of files, in a set of files. And then we can resume it later from that point after some time, and it's going to run exactly the same as it was during the time of the freeze. So it's fully performant. It continues running from the same point. The checkpoint actually can be created at any time, but the general recommendation is to do this when it's safe, when the application does not perform any transitions, etc. And when restoring it, it will deliver peak performance immediately. And this interesting logo at the bottom of the slide is CRaC, which stands for Checkpoint Restore in User Space. That's a Linux project that helps this magic to work. That's under the hood. It's a Linux C library that facilitates this implementation of the checkpoint and restore features in for Linux. So as CRaC depends on CRaC, it comes bundled with it, but on the other hand, you don't need to install it manually. Unfortunately, CRaC has been designed with to be independent of the underlying operating system, but still, as it's relying on CRaC, it's not yet. So you can use it on other operating systems, but it will have some dummy implementation. Let's have a look at the CRaC API. The CRaC project is highly focused on developing this Java API to enable saving and storing the state of the JVM, also together with the running JVM application. So it all goes around the coordination of resources. So during checkpoint and after restore, they wanted to make the application aware that it's gonna be checkpointed, and after it's gonna it has been restarted. This application interface is quite straightforward, so it does not impose any major restrictions except one, and that is that the application must not have any external connections during the checkout. So it actually provides a way to notify Java programs that they are going to be checkpointed and that they are being restored. So the coordination enables the application's code to react, so to adapt to that is going to be checkpointed, and to adapt to changes after it's restored, because this is necessary to have a safe checkpoint, so it can be safely isolated from the environment it's running in, and also to be safely restored, because many things can change in the environment, or we can restore the app even on another server, for example. So in general, the CRaC API and the coordinated restore at checkpoint project somehow non-disruptively try to introduce these new two phases in the Java application's lifecycle. So whatever is there now, we will have additional before checkpoint and after restore. All major Java frameworks currently are adopting CRaC, like Apache libraries, but also Micronaut or Spring and Spring Boot as well. And all we need to do is to include the org.crack dependency in the build file and start using it. So in case that the underlying JDK does not have CRaC features enabled, then this will just perform some dummy operations, and that's it. So once again, to mention that the OpenJDK project CRaC is like a development branch, so this API is still being developed, so it's not included in any JDK release yet. Okay, so let's have a look at the two most important interfaces in the CRaC API. So those are the resource and the context interface. As I mentioned previously, every external connection needs to be closed. That's the only restriction when using CRaC. So our objects that we consider that are resources that have external connections need to implement this interface. And when overriding two methods, so before a checkpoint, we need to free any used resources and then load them again after restore. I will show more examples later on during the demo. And then the third step is to register the resource in context. So it can be any context, but here I'm using the global context from the core library. But we can also, of course, define a custom context. So a context can be understood as just a container for resources where they get registered, and it then calls these callback methods. It actually notifies the resources in the same order before a checkpoint, when in the same order as they were registered, so before checkpoint, and in the reverse order for after checkpoint, after restore, sorry. As you can see that both methods throw exceptions in case that checkpoint or restore cannot happen successfully, so that can be handled. So if a checkpoint fails, the application will just continue running. And I will try to sum up some of the benefits of the project CRaC. So there are many, but the most important is that in general allows immediate application start with peak performance. So this was from a long time ago. It's been a pain point of Java's slow startup time and really time to achieve this peak performance. With that, then we can have faster deployment process. We don't need to wait for an app to start and to run. And it makes it very attractive for using in microservices, in cloud architectures, also in serverless computing, etc. So there's no JIT compilation overhead once we start an application and then let it run and warm up. Then when restoring it, all that is already been done.
Hey, Goran, we have a question here in the chat. So maybe you want to take a look. So is there CRaC in other JDK builds like Aves, Corretto, or Temarin?
Maybe in AWS Corretto, I'm not sure about that. For now, I know that there are early access builds available only from the CRaC on the CRaC official page, so provided by Azul or in Azul Zulu builds. So that's the only that I'm aware of, but I haven't checked for AWS. I'd say probably they are currently working on it, as it's quite a new project, but I need to check that. Yeah, but good question. That's perfect, as it's very suitable for serverless computing. I'd expect that it's over there. If not, probably that can be configured. Okay, so to continue for using in cloud and Kubernetes environments, it's good that we can benefit as it actually allows us to scale resources to meet the demand. So we only pay as we use, and the resources are up and running for a shorter amount of time. And as mentioned, it's ideal for applications that require more work during startup and warm-up time. And yeah, as you can see, everyone is now adopting CRaC, so I believe also Corretto and other JDK builds should have this soon. But still, I will mention here with the limitations. It's only available on for Linux, so as it depends on Cryo, and there are several other limitations like so no open external connections, and they won't be closed automatically when performing a checkpoint. So that needs to be done manually. We need to take care of that. Although in some cases, some applications or some frameworks do not require that much code changes or not at all. When restoring an app, it needs to be the same architecture. And when we restore after some time, if we rely on the system clock, and the time difference might impact application behavior. So that should be, we should keep that in mind, as we might want to invalidate some caches or perform some additional updates if needed, or to sync instances, for example. So here's a quick summary of some pros and cons of Project CRaC. I wanted to have it here visually to list, and then later on I'm going to compare it with GraalVM native images. So it literally provides just instant startup, great performance right from the start, and it's still a JVM, which is great. We can keep the JIT compilation optimizations. We can also debug it and whatnot. But on the other hand, there are several downsides, like restrictions. In order to use this great feature, we need to start the application once, and then it needs to be warmed up and then saved and then restored. So it's a few additional steps. Also, from the security point of view, some sensitive information like private keys or some passwords, if they are loaded into memory inside the app, might leak into these snapshot files, and they might be read if they are because they are available. So it can be easily done. It can be easily fixed by just getting rid of it before performing a checkpoint. So it's not a big deal, but there are several things to keep in mind. And let's see how this compares with GraalVM native images. So Project CRaC is just an alternative to this approach to GraalVM native images. So this is GraalVM native images offer ahead of time static compilation. So there's no runtime compilation of the code. So there's no interpreting bytecode hotspot analysis or CPU load, additional CPU load. And then, so it's very fast from the very start. It's much smaller memory consumption and a much smaller image than the snapshot itself. So that's great, but on the other hand, we need to have all classes available at the build time. So the build time might take a lot of time to succeed. It's not anymore just a few seconds, but it probably goes up to 5 or 10 seconds to have a successful build. Also, it's quite error prone. It's quite requires some deep knowledge, some configuration, might cause some developer frustration because we get error after error. Also, we lose the JIT runtime optimizations as well. Some performance numbers show slightly lower performance than the JIT optimized JVM that we get with Project CRaC, so about 40%, and many other things which are just done differently. So Project CRaC is solving almost the same problem, but a slightly different approach. And let's have a look at some numbers about Project CRaC. So here are some proof of concept results with several different frameworks, and the Java application that's using Spring Boot and OpenJDK without Project CRaC takes about 4,000 milliseconds to start. So time to first operation. The same application, when checkpointed and restored, takes 38 milliseconds. So with CRaC, it gets down to 38 milliseconds, which is just like really mind-blowing. Let's say a good use case would be to have, you need to handle an HTTP request. We want to fire a function in a cloud provider. Then we would be able to do it in less than 50 milliseconds, and then just shut it down, and then a request is served, and all good. The same goes with other frameworks as well. And on the graph on the right, we can see that time to complete M operations for Spring Boot is also quite lower. So if we have 100,000 requests, it takes about 43 seconds to serve them with OpenJDK. With OpenJDK on CRaC, if the application is properly warmed up and then restored, we get that peak performance right from the very start. And in general, it's a much faster response. So we get about 5 seconds lower response time, which is, of course, very beneficial. Okay, so how do we checkpoint and restore an application? Let's see some of the commands and some of the parameters. I've mentioned this very simple example here from the command line, where I built the app.jar file and I'm using the java-jar to start it. There's one additional parameter that says where to checkpoint the CRaC files to. Here I can specify a relative or an absolute path, and the application will start and continue running. Once that's warmed up and we are satisfied with its performance, we can then initiate the checkpoint. The checkpoint is initiated using the J command. So there are actually 2 ways. One is so-called external way, and then specify a PID or an app.jar file, or the full path of the jar file, and the jdk.checkpoint parameter. If it goes well, if it's successful, the application will shut down, it will stop running, and we will have the CRaC files available here. On the other hand, there is an internal way to do this programmatically using the core library from org.crack, and then we can initiate it with checkpoint restore. This can also be initiated from outside, of course, but here is a simple example of how to do that. And then we can use the CRaC files to restore the Java application from there. It will start immediately and it will continue running from that point. And that's all about the presentation. I would like to switch to the demo if there are no additional questions about the technical information and how this works. So the first one, yeah.
So far, I don't see any questions, but we have a Q&A at the end, and maybe also after we've posted the video. But I think we can move forward to the demo.
Yeah, cool. Yeah, probably. There might be some questions about the demo and these examples. So here's a simple example that contains 2 classes: the main class and the server manager class. That's also the resource. And here I've tried to simulate a Jetty server that listens to opens a certain port to listen to requests and then send some response back, some messages back. So the application itself has an internal request counter that starts from 0, actually from 1. It's an abstract handle that sends a text message back, and it then increases this counter. When it started, it actually tries to simulate some heavy lifting, but it simply just sleeps for 10 seconds, and that's all. After that, it's going to start a server manager. It will open port 8080, and it will use this request handler. That's all, quite simple. I think it's easy to understand this. On the other hand, the server manager is a CRaC resource. It has an internal Jetty server that started on port 8080, and it's registered in the global context as a CRaC resource. So we need this in order to receive checkpoint and restore notifications, so we can close that open port because that's a requirement. And simply before the checkpoint, we close all open connectors because they can listen on several ports, and after the restore, we start listening on those ports again. That's all. So here I have a simple, yes?
Goran, I'm just thinking maybe we could do the letters a little bit bigger in the sense of 150 or something. I'm just thinking about the video. It's clear. We can see it nicely, but maybe if we could.
Sure. I will
just a little bit.
Zoom in a bit. Let me find the option.
But not necessary. I was. Milan Slavic said maybe presentation mode. Yeah. Yeah, I think now it's a little
fine. Okay.
Thank you, Milane. Thank you, Goran.
Okay, cool. So here I have a very simple script to fire a request to this port 8080 on localhost every second. And if I start the script, I will see that it's nothing there. There's no response that to get this back. I'm going to start and first build this application using the script, and I will start it as previously mentioned using this jar file and configure that the checkpoint should go into this directory, so it's a relative path. If I let it run now, the application will be build and start in about 10 seconds as it kind of performs some heavy load. After 10 seconds, it's going to start listening on port 8080, and if I check the request, I can see that it's now getting some results back, and it's increasing the counter. And let's say we're now satisfied with its performance. We want to checkpoint it. The checkpoint is done using the J command, and then I'm using the jar file and the JDK parameter. If I execute this, it will say, okay, this is the PID, and the checkpoint is finished. I will check the output of the application itself. So it was running up to this point when the checkpoint started, and then I get some output here as to confirm that everything finished successfully, and CRaC files are saved here. I can also show you that it's there, but not too interesting. So there are many files that are listed here, and now we're going to use those files, so it contains the full JVM warmed up state from there. If we check the request script, it's now firing requests every second to port 8080, but there's nothing there. So I'm going to do the restore from these CRaC files using the Java command. Let's fire it up, and you will see that it instantly started listening on port 8080, and then it also got the response back. And you can notice that it started the request counter from the very last count that it was before the checkpoint. Yeah, so that's all about this simple example. I'm gonna shut it down, move on to the second one, which is that one about the CRaC writer. Here, I'd like to show how we can react to how we can actually programmatically perform the checkpoint and restore. So it's a simple writer to a file. It's going to append some text or messages to a file, and then it will log a lot of data before and after it does these operations. So here we can see that the main method starts writing to this using this CRaC writer resource. It appends a message before the checkpoint, does perform programmatic checkpoint restore, and then if we initiate the checkpoint, it's gonna actually perform the checkpoint automatically. If we initiate the restore, it's gonna continue running from this point. So quite simple, and the resource interface is implemented in the CRaC writer resource. So again, we need to register the resource in the global context, open the file writer, write to it, append some messages, and then close it. Before the checkpoint, I'm gonna log that before checkpoint for this resource was called, and then close the resource. After resource, log the message and then reopen it. So let's check. I'm gonna just remove the files so that we have a clean situation here. And then there's a script to watch for this file, but we can also open it. Let's start the checkpoint. So this is going to perform Maven clean build, Maven clean package to build the jar file, and then start this application. So let's see. Here we can see that within 1 second, the build was successful. We are using Java 17 CRaC version. and then it initiated a checkpoint before the checkpoint for this resource was called, and it's successful. The checkpoint is done, and the application was shut down. That's the default behavior. Now we can check the output file. It's over here. I'm going to move it to the right. And then let's see what happens if we initiate the restore. Now we see that the restore, after restore was called for this application, so the PID is logged here, and there is a new message appended to this one, so line 2 InterVenture after restore. Let's say I want to restore this application again. It continues appending to this file as well, because that's how it's configured. And so this is not about improving the performance, but showing how it can programmatically execute the checkpoint and restore, and then continue running the program from here after it's restored. Then the third example is slightly more complex. I'm gonna show this, and first let me explain it. It's about the prime numbers cache. This program actually has a loop that executes every 5 seconds. In that loop, it will check 100,000 times if a random number between 1 and 100,000 is a prime. We, of course, know what the prime numbers are. So before this program does the calculation, it will check whether the result is in the cache, in the local cache. If it finds the number, then it will instantly return it to the caller. If it's not there, then it will calculate the result. So it requires some time to do that, put it in the cache, and then return it. So you can, of course, anticipate this at the beginning. The cache is empty. It will require some time to fill in the cache. And with every other iteration, every 5 seconds, it's going to fill in the cache more and more. And after some time, we're going to have completely full cache and instant performance for all 100,000 numbers right away. So let me start the application using this start script. It performs greater build. Is there a question? Yeah.
Yes, there is a question from Nicola. Is there an option provided by CRaC which prevent application from termination when the checkpoint is created?
At the moment, no, but it's quite often asked to ensure that. But so far there is not. I will show later on in the last slide what's the typical deployment and the release procedure for this. So might be clear why that's done and how that's done. I've not, as far as I know, there is no option, even though they say that's a default option, but they do not state how to configure this differently. So to let it run. Okay, I would also love to have that option as well. Okay, so to go back to this example, so I'm starting the application. JVM startup time, as you can see, is very fast. It started in 30 milliseconds. There are 2 resources that are registered here, and we are performing several runs. You can see that cache, while I was talking, it has filled up to 100%. So it took about how much? 10 runs to fill this. And we can say that we are now completely satisfied with this current state. We can initiate a checkpoint, and the checkpoint was successful. So let's see what happened here. When the checkpoint started, application warm-up time up to this point was 86 seconds. So we can see that it was almost 1.5 minutes before this application while this application was warming up, and then we decided to checkpoint it. So it was shut down, and from here we can then say, okay, I will restore it on a different machine. We can take these CRaC files again and use it to restore using the same principle. If we restore it, you will notice that now it's the 19th run, but the cache is completely filled. and it started almost immediately, so there's no waiting time for this. So I guess you got the idea, you got the principle for this. I'd love to show you just to go back to this first example with Jetty, to show you how to start the application and initiate the checkpoint exception. So we'll comment this out. So we're not going to close resources. Let's start the application using this script. It's going to build, run, again, wait for 10 seconds. And there's no exception now, of course, everything is okay. I can fire the request. I can see that it's starting to respond. 1, 2, 3, good. It's still running. If I initiate the checkpoint now, it will say, oh no, for this bid, it cannot be done. The checkpoint exception prevented this application from being shut down and creating the checkpoint files because the socket was open. So for port 8080, you need to handle this first. And the application is still running. Of course, you will get more log messages here. And I think I have more examples how to start this here. So in case there's something wrong and you want to debug more information, there are additional JVM parameters that can collect more stack traces or unlock some specific VM options, also to log the JDK trace, startup time, etc. So quite useful if in case something goes wrong and you need to figure out what happened then. Yeah.
There's a question.
Yes.
What happens with direct off-heap memory when checkpoint is created?
Direct off-heap memory when checkpoint is created. Well, as far as I know, everything is saved and then reloaded, but I'm not sure if that's what you're referring to, I guess.
Let's
see. The question. So literally everything that needs to be, that's currently in running memory, that's required to restore the same application state will be used. Off-heap memory. Oh, I see now. Sure, I need to check. Yeah.
Yes, I can also write it down,
yeah.
then we can come back to you, Milan.
Yeah, but thanks. That's
an idea. Lovely.
Yeah.
Mm-hmm.
And I promised to share the last bits and pieces as Nicola asked. I think we can. What does it need to be shut down? What's that default behavior, and how we can actually release this? Let's say we created some Java artifacts, for example, Java jar files, and then it's usually deployed to production instance via regular CI/CD pipeline. The production request hits this instance, and it's all good. But it takes some time for this instance to be warmed up to start, and we can introduce another pipeline here, of course, with canary deployments, and then the canary requests. So we can let this instance heat up to warm up, then perform the coordinated checkpoint at some time, and then receive or create these CRaC files, and then use these CRaC files that have everything saved, so the class loader, the JIT optimized code, and everything that's already there and running, and then perform the coordinated restore and to deploy it to production. So this is going to start instantly, and it's going to have highly optimized peak performance code from zero, from second zero. And there's just one example how this can be used. I see there's another question. I'm going to read it out.
Yes, there is another one. Do you want me to read it?
No, I will do it in the presentation. I noticed that there is an improvement when the application running in Kubernetes. When we make snapshot, an app will shut down and Kubernetes will restart pod if Linux Pro is set correctly. How will we get the improvements? Okay, so it will restart the pod. Well, I guess that can be solved by just saving this to a volume. It doesn't matter that it will restart the pod. That's all fine as long as you get what you want with the checkpoint procedure. So then you can use these artifacts that are created through checkpoint to restart that pod, to configure it, or not just that one, but the whole replica set to use this warmed up instance. So it's like a frozen state at some point, and then I guess that's if I understand the question correctly. Not feel free to write and correct me if there's anything additional.
If you have another question, and I'll write this one also down so we can go back to the guys and with some answers once you check something. So.
Yeah, of course. And great questions, by the way. I'm really happy that you got the idea. You are asking some very specific things about the cloud environments and this super fast genuine startup. Even though it seems like a simple idea, it does take a lot of effort just to put it into practice for your environment. So that would be all from my side about this project CRaC. So it's in general, I'm quite excited that it allows us to have a very performant applications run right from a simple snapshot, and that we can eliminate this need for hotspot identification, even though as developers we don't care about that much because we run everything locally and don't care that much about production in some cases, or we're going to put more resources into it if it takes several seconds more. But let's see what the future might bring. Of course, I hope that sometime in the future we'll have like fully complete production examples with the databases, with a whole landscape, and then we can really simulate how it works and then show some pros and cons of that.
Had a nice comment in the chat. Goran is also very active. Thank you so much. Or to create snapshot in CI/CD and in KH, use only restore point. So it's quite a nice discussion we have here.
Okay, yeah, you are more familiar with Kubernetes. Haven't worked with it for a year and two now. Need to recall some specifics, but of course, yeah, good point. Thanks. I'm gonna stop sharing. That's all. Yes. Thank you for your attention.
That was lovely. Thank you so much, Goran. Also, the links that you shared, I will also share in the email, follow-up email. Milan Savic says, nicely done, which I agree. Thank you so much. Also, Branislav. Yeah, so thank you so much, Goran. I'm just going to stay a little bit and see if anyone else has an additional question, some remarks, anything besides a lot of applause for Goran. As I said, we will be uploading this video also on YouTube. I will be sharing in a follow-up email exactly also the slides and also the GitHub and everything that you shared. So great presentation from Nicola. Yep, it is a great presentation. So thank you so much for your time. It really means a lot, this knowledge sharing. And I'm very excited that there are people that are actually also writing me and telling me that they've been going to tackle these things on their own project here at InterVenture. So I was so free, Goran, to also suggest that if they have any further questions or any challenges that they can write you, because that's what this is all about.
Yeah, of course. Don't hesitate to reach out. I'm available to. I'm looking forward also to hear your experience with this if you plan to play around with it.
Yes, so we can also exchange some examples as well. And then, I don't know, Goran, I liked it a lot. So maybe you will join us for another webinar, who knows? But this was a great job.
Yeah, of course, we can plan the part 2 somewhere next year.
Yes, who knows what the future will bring for this topic. But yeah, a lot of nice. But if there are no questions, I would say we just spot on ended this webinar. So once again, thank you everyone who participated. It really meant a lot, and also very interesting questions. So thank you for engaging, and obviously thank you, Goran, for participating. Thank you for sharing your knowledge. It really means a lot, and really nice having you here at InterVenture. So thank you so much, and have a wonderful evening to everyone here.
Awesome. It was my pleasure. Have a lovely day. Bye-bye.
Bye-bye, guys.